Okay, what's going on, guys? Hope you guys had a fun holiday weekend. Nice little break. What's going on, Sib? Did anyone do anything super exciting for July 4th? I ate a lot. I cooked a lot of food. That's what I did. Probably got a picture of some food I cooked at some point. Ooh, yeah, this is what I cooked. Some chicken, hot dogs, short ribs, corn. Oh, I was at a friend's place. They made like this awesome like corn and like cheesy potatoes, chili. I love all that stuff. Came back to UCLA. Okay. Prof is a chef behind the soundboard and the kitchen. Appreciate it. Sophia says, in the Cootie chapters, there are all the sections, and then there's some that further reading. No. If it says further reading, you don't have to know that. No. I mean, if you want to read it, yeah, go for it. But I'm not gonna like trick you guys with stuff. I know some professors are super mean, and they like hide what's going to be on the exam in like weird places. Like, no, I don't do that. I don't believe in that. As long as you understand like what's going on in the homework, what we do during lecture, and what you do during discussion. Oh, I forgot to mention that but yeah, discussion. Discussion is very important too. But I think that's kind of self-explanatory, right? Anything you do in discussion is usually like fair game for an exam. But okay, yeah, our first exam will be on Friday. I put an announcement about it out on Brew and Learn. It'll be on Kudu, so except like you won't get like a check answer function, obviously, because that would be kind of pointless for an exam. But we're also gonna have you, you need to show your work on another piece of paper, and we're gonna have you upload that. I'm talking to Albert, your TA. I think we're gonna have you do that to Gradescope. Which y'all should all be pretty familiar with how to upload things to Gradescope, I hope by now, because that's how you've been doing your discussions. So, yeah. Should be pretty familiar. I'm going to give all day for you guys to do it. I'll release it when we usually have class, but then you have, like, the rest of the evening up until, like, yeah, whatever, midnight to submit things for it. That's for the exams. I talked to the department, and they heavily recommended that I don't do that for the final. So I'm sorry, but for the final, they really want me to give it during the time period. I think they're a little worried if I just give a final out and it just sits out there for like 9 or 10 hours that everything just goes to chaos. And I was like, okay, guys. So yeah, the final exam, unless you have like some extreme case that you can't make it, but also it's been on the calendar since you signed up for the class. So, but please try to, clear that out. That's a month away from now, but please try to clear out that time slot for the final. You get whatever I can give you a formula sheet for sure. I mean, the test is open book. It's open notes. It's open whatever. Just don't use AI, please. Yeah, don't do that. Like, I can tell if you're using AI, and some of the questions are specifically written such that if you do use AI, I know you used it because you'll get the wrong answer. And it's not a good look, I had this last quarter. I had certain students that would last minute get, what do you call it? The Center for Accessible Education, the CAE stuff, right? And I could instantly tell that once their grades were going up like an insane amount and like their responses started looking near perfect, I was like, okay, I know what's happening. You didn't just instantly, get super knowledgeable in the subject overnight. The testing center is allowing you to basically cheat. But your professors can always tell when that's happening. So if you're trying to get like letters of recommendation or, stuff, don't do that. I had one student who was like, yo, can you like bump me up like a couple points? I'm like, bro, what? No. Like, first of all, I heavily suspect you're cheating, and I don't want to go through the paperwork of filing it, but don't get super greedy and start asking for more points. For the final, no, I think you get 3 hours for the final. I want to say the final is like 3 hours in length. Yeah, still show your work for multiple choice. The reason being for that is, so, you know, Kudu will tell you right away it'll tell me right away once the exam's over, whether you got points for the question or not. In the case that you don't, we're going to have you then submit a request for like partial credit. So if you feel like, hey, I think I should get some partial credit on this question, you can then submit like a partial credit request, and then we'll go over the work you submitted and like make sure that, you know, we can get you all the points you want for that. Wait, can you use AI in CAE? You're not supposed to. But I believe me, bro. I know that testing environment. I mean, no shade to CAE, but like sometimes it's not proctored the best, and people can just they can finesse. I know people can finesse things when they're not like in a classroom and being watched, you know. The exam is on Kudu, but it's on both, Sophia. So you submit your answers on Kudu, you submit your work on Gradescope. That's how it works. So, you know, if you want to do everything on your own sheet of paper and just at the end just like transfer over what your responses are on Kudu, totally cool. You can also like do it simultaneously if you want. But yeah, your score will get registered through Kudu, and then we'll use your work from Gradescope to make sure that you're not just blatantly cheating, and also to anytime if you want like partial credit for something, we'll check what you submitted on Gradescope as well. Will we insta get the scores? You insta get the scores once I close the exam, yeah. But I'm not going to close it till midnight because I'm going to give people the rest of the evening to do it. Because I understand it's the first exam. People probably a little nervous on like, how do I connect to the internet? How do I make sure? I don't want people being like a super crazy time crunch. So I'm giving people a lot of time on the first one. I'll probably do the same thing for the second exam. The final exam, they're being stringent about. I'm not going to go so far as to start requiring lockdown browsers because I hate that stuff and it's just annoying. And again, we went over this before. Like you want to test yourself. You want to make sure you're understanding stuff, because when you take 1C in person, then you're in a classroom. And a lot of what we do here in 1B bleeds over to 1C, because how the class is structured, we cover like half of E&M during this, and then you do the other half, like the magnetism part, in 1C, and they're very connected. We're going to start E&M today. So it's very important that you actually learn and understand what's going on in this class if you want to do well in the next class. So yeah. I 100% recommend taking 1C right after this. Yeah, very much. I would definitely do that. I'm not saying you have to take it like the next summer session. You don't have to take it like literally the week after. But if you can take it in the fall or at least the winter, I would, because a lot of what 1C covers directly connects to 1B. 1A to 1B, not so much. It's not a crazy connection. I mean, there's a little bit with the simple harmonic motion, but 1B to 1C is very connected. It's just how they split E&M. I personally would not split E&M between 1B and 1C. I would have made E&M all 1B, so the electrostatics and the magnetism parts, and then I would have shifted the wave stuff over to 1C, but, you know, that's just difference of opinion. Anyways. Okay, cool. Enough of me discussing my opinions on class structure and stuff. Corbin's the only... Yeah, you guys say these things about Corbin. He's a good lecturer, right? I do remember when I met with him being like, my exams are tough. Which, yeah. But I think he curves, so... Well, he has to curve, right? Anyways, yeah, I'm currently not scheduled for the fall due to whatever, like, budget crisis UCLA is having and, like, I don't know, like, federal funding getting withheld. But I still... will always have kind of like my office hours through my nonprofit. So if you're taking 1C with another physics professor and you're having trouble, but you still want to get help from me, totally can. It's free. Like, I'll continue doing that in the fall. It's the same schedule. So I can't make your exams or grade for you, but I can still help you out. Yeah. Yeah. Corbin, he's a good teacher, Corbin. He's a good teacher. I know. I've heard the rumors of his exams are hard, but it's okay. Yeah, you're welcome, guys. Okay, cool. All right. That being said, let's start off the lecture. So, welcome to week 3. Wow, we're halfway. Lecture 1. Cool. And we're going to go into the fun stuff today, which is starting electrostatics. So electrostatics refers to basically like what's happening with electrons or like charges, charged particles. That's the main thing that all and the static form of it means that things aren't really moving. So when we get into like electrodynamics, that's when we have like changing electric fields or particles that are moving in time. Electrostatics refers to things that are just kind of like staying still. So, see, things I want to do. Yeah, we can talk about some charge stuff. I really want to get to like just like calculating Coulomb's law, but anyways. So main thing, yeah, charge is quantized. Quantized, you'll learn this in like quantum mechanics. It just means that things happen in like steps. So charge comes in like certain steps, and usually it's in like the number of electrons you have. And so the smallest amount of charge that something can have in the SI system is the charge of an electron, which is equal to 1.6 times 10 to the negative 19 coulombs. Coulombs is the units we're going to use for charge. So yeah, you can't have anything with less charge than this because then you'd need to have like partial electrons, which unless we're talking about like subatomic particles, doesn't really work. Cool. Yeah. And that can be the smallest negative charge, or that can be the smallest positive charge. If you've taken chemistry, right, you learn that things can have positive charges if they're like ions, and that happens when like you lose electrons and there's more protons. But yeah, the universe, the way it works out, smallest unit of charge that can be positive or negative is this 1.6 times 10 to the negative 19, which we'll sometimes just write as like E, like little e. Charge is conserved, right? You can't destroy charge. You can't convert it to friction. Charge is constant in a system. So if you do have loss of charge, it had to have gone somewhere. And usually that's through like grounding, like through the earth or whatnot. And we're going to go over that. That's a cool thing called charging by induction. So, some water. All right. So sources of charge. Charges come from electrons, right? You guys probably learned this in chemistry, I would imagine, right? So you have always a nucleus that is filled with like protons and neutrons, right? And then you have this cloud of electrons. We tend to simplify this, right, by thinking that the electrons exist in these circular orbits, and these are like energy levels, which, if you remember from when we were doing, what was it, like the allowed modes, those kind of represent the same like energy levels, like n equals 1, n equals 2, n equals 3. But in reality, electrons don't follow these nice perfectly circular orbits. They're actually kind of more like a cloud. It's a probability distribution that, you know, they're most likely to average out to be on this ring or not. And yeah, there's a lot of history of like who came up with this. There's like the plum pudding model, all that fun stuff. But again, this is not a history class, so I'm not gonna be like testing you over. Well, Rutherford said what? Or Thomson said what? That's was it Physics 10? Physics for Poets? I think there's one of these, right? There's like kind of a physics class at UCLA that doesn't really require math. Or it's like really chill on the math. That's more kind of metaphysics history lesson. Okay, conductors and insulators, right? Yeah, so we have two different like classifications for materials. We have conductors, which allow for electrons to move about and like kind of be free. And this allows you to like move current through these things. You can have voltages, and they're also usually like pretty good like thermally for like conducting heat. So most metals are conductors. And yeah, these are what allow electrons to like move around. Insulators do not allow electrons to really move around. And so they're not really great ways to, you know, draw current. They're not really good ways to move charge. Some examples of that, right? Yeah, wood, glass, plastic, the air. The air is a pretty good insulator. Unless you have such a huge charge differential or voltage difference that you get lightning, or you can get like arcing. But yeah, insulators do not allow electrons to really flow. Conductors do. Okay, so one thing we can talk about is charging by induction, which is pretty cool. So let's say, for instance, you have a glass rod and it has, well, here, let's say, for instance, you just have a sphere here. And let's say that it is a conducting sphere, okay? Conducting means that the charges are allowed to move around and stuff. So let's say we have a conducting sphere. You would expect there to be kind of an equal mix. If it's neutral, let's say if the overall charge of this sphere is neutral, you would expect there to be an equal homogeneous mix of positive and negative charges kind of chilling around. Notice that, right? The overall charge here would be 0 because you have like 4 positive charges and you have 4 negative charges. Okay? Now, because these things are conducting, the electrons are allowed to move around the sphere however they want. And one thing that we're going to learn when we do Coulomb's law is that like charges repel each other, but opposite charges attract. Okay? So we're going to say, like, you know, opposites. You probably heard this before. Opposites attract or something. Opposite charges attract. And then we say, like charges repel. So, for instance, if you have a positive charge and a positive charge and they're next to each other, and we're going to go over this with Coulomb's law, they would each feel a force that would be repelling them away from each other. And let's say, for instance, this is particle 1 and then this is particle 2. I would say this is like F1 on 2. And then this is F like 2 on 1. It turns out when we do Coulomb's law, we're going to see that these forces are equal and opposite. So the force that charge 2 here feels from 1 pushing it this way is the same force that charge 1 feels from 2 pushing it this way. So they don't want to be close to each other, but yeah, they repel each other, and their forces are equal and opposite. By the same token, if you had, let's say, 2 charges, but they were opposite, okay, let's say you had a positive charge here and a negative charge here, okay, now they would feel an attractive force towards each other. So this positive charge here would be drawn towards the negative, and the negative charge would be drawn towards the positive. And same thing here, F21 would be equal to F12. Just different directions. Good so far? Any questions? Looks like my internet's holding up today, which is good. Let me know how bad the latency is. I spent the weekend actually installing like a pretty big antenna in my apartment to try to get better bandwidth on stuff. And I think it's doing okay so far. Okay. So now, so here's what so let's say, again, we had our conducting sphere here, right? And it was neutral, and the charges are moving around, okay, free. But let's say we bring a positively charged glass rod next to this neutral sphere, okay? What we know, right, is that the opposite charges are going to attract to each other, right? So this rod has like a bunch of positive charge on it, okay? And so what happens is when it gets close to the sphere, it's going to pull more of the negative charges towards it. Okay? So now what you get is this is called like a polarized sphere because it has different polarities or different charges on each side of it. So now on the left side of the sphere, which is closest to the rod, that becomes more negative because these negative charges are being attracted towards the positive from the rod. And the positive charges within the sphere are now getting repelled. And so they get forced to the right side of the sphere. Okay. So this is a way to kind of like polarize a conductor, and you're not even touching it. And now here, I'm going to show you a cool thing. You can actually use this to change the charge of the sphere by not touching this rod to this, but by doing some other stuff with like grounding. Yes, this is also called a dipole. So whenever you have like a positive and a negative side, this is called a dipole because it's dipolar. I mean, you have two polarities, right? You have a negative side and a positive side. Yeah, two ends, two poles. Okay. So, did I do the grounding rod? Yes, that's what I want. I want the grounding rod. The grounding rod example is really cool. And then we'll let me copy this image in. Okay. So here's an example for how you can what we call like charging by induction. So, for instance, if you had a positive rod here being brought towards a neutral conducting sphere, the negative charges would congregate on one side, the positive charges would congregate on the other. Now, if we connect this sphere to ground, ground is just referred to like as the earth. The earth is seen as like an infinite bank of like positive or negative charges. It provides whatever is needed to like neutralize something. So in this case, when we have the positive charge from the rod pushing the positive charge from the sphere like away, those positive charges are going to escape through the ground to the earth, because the earth is like this. Again, the earth is like this massive sink that will just accept, stray positive charges or stray negative charges. If the positive charges don't want to be here, they can leave. They can go to the ground. And so when they do that, right, now the sphere doesn't really have much positive charge left on it. Really what happens is the negative charges from the ground are kind of like attracted out of the ground into it. This comes to the fact that like positive charges don't really move. It's really the electrons that are moving, and whether there's excess electrons or like a lack of electrons, that's what creates like negative charge and positive charge. But you can still think of it as like, oh, the positive charges are leaving. So once the positive charges have left and we disconnect the sphere from the ground, let's say we just cut it right here, right? Now, the sphere only has negative charges in it. And when I remove the rod away from it, now the sphere has an overall negative charge on it. So this is a way to induce charge within a neutral object without ever like touching it with the charged rod. You can just get the rod close to it. You can push the positive charges out. You can give them a way to get out with a ground. And then as long as this is still next to it when you cut the ground, then this will leave like a negative charge on it. If we move the rod back away, right, then the positive charges like come back up, and if the ground is still connected, and so then it would be neutral. What you're doing is you're forcing them out, you're giving them a way to escape, you're cutting off the escape route, And then once you remove the charged rod away, it's left to be negative. So, yeah. Let me know if that makes sense to you guys. That's called charging by induction. Good. So the sphere was neutral to begin with. So if something is neutral, it means it has an equal number of positive and negative charges. Okay. So neutral means an equal number of positive and negative charges. So that if things have zero charge, starts with bunch good. Yeah, positive, negative. We push the positives out. We don't let them come back, and now the thing is negative. That's how that works. So yeah, this is what's called like charging by induction. Okay. You can also do charging by conduction, right? Which is just like touching charge to. If you have like two conducting things, and like let's say for instance, you took the rod and you just attached it to the sphere, that would just manually allow the charges to move. So there's another one here. So let's see. Yeah. They don't do an example, but I'll write one. Okay, so let's say like charging by conduction. Okay, so if, for instance, let's say you had a rod here that had, I don't know, let's say like 5 nanocoulombs of charge on it, right? And then you had a rod here, sorry, a sphere that was neutral. Well, here, let's just copy our neutral sphere again. Yeah. So what happens, let's say again, this is at 0 nanocoulombs, okay? If you get this rod to touch the conducting sphere, then what happens is that the excess charge from this will average out with the sphere. So once these things are touching each other, okay, you actually get the transfer of charges between them. So let's say once they touch. So if they touch, now what happens is some of these negative charges will start moving over here to try to create the most balanced system you can get, okay? And in that case, you're going to get 2.5 nanocoulombs here and 2.5 nanocoulombs here. And then what happens if you were then to separate them, right? You have them touching. I would say like averages out the charge. And then if you were to separate them later, then now this would have 2.5 nanocoulombs, and this would also have 2.5 nanocoulombs. So again, I'm not going to draw like the number of charges to scale, but just know that it would have a couple more negative charges around it. Whereas this one would now have more positive charges on it. Yeah, so let's put like some extra positive charges. Yeah, let's say this is a conducting rod. Yeah, and this, again, only works if these things are conductors, because conductors are what allow charges to move in between them. So if this is a non-conducting rod, then charges won't move. Okay? So yeah, that's charging by induction, charging by conduction. Let's see, I think there's a clicker question related to that. Let's go check that out real quick. So if we go to refresh, I think it's the third clicker question. There we go, lecture 9. That's Coulomb's law. We'll do Coulomb's law in a second here. Okay, here we go. This is good. Let me get the answer choices. This is for 9. So this is question 3. By the way, it's not the first one. This is question 3. But okay, it says we have 3 identical metal spheres. So metal spheres, right? This means it's a conductor. Initially with their own charges. So this one is at -5 nanocoulombs. This one is at +8. And then this one is at -4. And they say spheres B and D are touched together and then separated. And then spheres A and B are touched together and separated. How much charge is on A at the end of this process? So this is 2 different charging by conduction because we're directly touching 2 conductors to each other. So when you have B and D touch each other, okay? Remember that when you have charging by conduction, the charges average out amongst each other, okay? So you had a +8 and a -4. So the average for that would be 8 minus 4 all over 2. So this would end up being, yeah, that would end up being 2 nanocoulombs. Okay. So this +8 and this -4 touch each other, and now you're going to have +2 here and +2 here on B and D. And then these 2 are separated, right? So they touch, the charges average out, and now you have this one separate from this one. And once they separate, the charges don't change. Okay. Now I take ball A, which has a -5 on it, and we touch these 2 together. Okay. So now A and B are going to touch each other. And when that happens, they average out their charges. So you have -5 plus 2 all over 2. And so that's going to give you -3 over 2, which will be equal to -1.5. So now the new charge on each of these will be -1.5 nanocoulombs. Okay. And then you separate them. And when you separate them, charges don't change. Grab it, please. There we go. Okay. And they were asking for how much charge is on sphere at the end of this process. Okay. Well, that's going to be the -1.5 nanocoulombs. So that should be answer choice A. Let's see if that's correct. Yes, good. Okay, cool, nice, we got that right. All right, does that make sense with the charging by conduction? So again, if you have like conducting things with different charges on them and then they touch, the charge on each of them will like average out to like what the total average charge is. So that's why the +8 and -4 became 2. And then the 2 and the -5 became -1.5. Nice. All right. Awesome. Okay. Let's keep moving forward. Okay, Coulomb's law. Yeah, Coulomb's law is nice. Okay, cool. And they have the fancy vector calc definition of it. Okay. Well, this is, yeah, okay. I'll explain, like, what all this math stuff means, but, okay. This is what we learned for Coulomb's law. So, remember from before, we talked about how opposite charges attract each other, right? And like charges repel each other. Well, it turns out that attraction and repelling is a force that we can quantify with a number using this equation. How I usually like to write this is that F is equal to K, and then we're going to say Q1, Q2 over R squared, where K is equal to 9 times 10 to the 9th, which, funny enough, that's the same thing, or approximately the same thing, as 1 over 4 pi epsilon naught. So you can either memorize this, the 1 over 4 pi epsilon naught. I forget what epsilon naught is. I think it's 8.85 times 10 to the minus 12 or something. Or you can just know that this 1 over 4 pi epsilon naught is the same thing as K. And that's 9 times 10 to the 9th. That's a decent approximation. You can use that on any homework, any assignment. It works out. Okay. Q1 and Q2, these are the charges of your objects when you're measuring the Coulomb force in between two objects, so the force due to them having different charges. And then R squared, this is the distance between them. Oh no, there's lag. Oh dear. All right, distance. Let me make sure. I think my signal should be okay though, right? Oh, okay. Distance in between. Okay. Let me see. Let me try. Oh, it's better, thanks? Okay. Let me know if it comes in and out. I hope it should be better. I spent a lot of time this weekend. I'll show you guys. Just real. This is actually kind of a this is a physics thing. I installed an antenna. This is what I was doing over the weekend. Installing some antenna to make sure I can like get better bandwidth. Okay. Let's see. All right. So distance in between the two charges is equal to R, and then these are the individual charges between them. Okay. Now, yeah. When they write it like this, I'm gonna explain like kind of where this comes from. No, not this. No. Yeah. So when they write it like this R hat here, this is a unit vector, which means it doesn't have any magnitude, right? Magnitude of 1. And this points in the direction from charge 1 to charge 2. What's up, distant fonts? Yeah. So that's what R hat is. You can also see, right, this is the same thing, K, Q, Q, Q over R squared. And then the key thing is that the direction it points is directly from your first charge to your second charge. And we're going to show how, like, sometimes that means you need to do things in terms of, like, components. Okay, cool. Oh, yeah, epsilon naught is 8.85 times 10 to the minus 12. Okay, so let's do a clicker question that kind of relates the charges between objects, but also when things are done in, like, 2 dimensions. Well, actually, yeah, let's do a 1-dimensional case first, and then we'll do like a 2-dimensional one. Let me find That's 2D. Where's like I want a 1D case. Oh, actually, you know what? Someone had a really good question. This actually in my Discord. Someone asked me one of these. One second. Let me pull it up. Where was it? It was here. Yeah, okay, cool. So let's say, for instance, a +3 nanocoulomb charge is at x equals 0. And a -1 nanocoulomb charge is at x equals 4, okay? Where should I place a +1 nanocoulomb charge such the net force on it to 0, okay? This is kind of a fun little question. Okay. So, always good to like kind of like draw like a little number line or coordinate system for like what's happening here. So we have some like x equals 0. And that's going to be a +3 nanocoulomb charge. So I'm going to say +3 nanocoulomb charge. And then you have a -1 nanocoulomb charge at x equals 4. Here, let's put a -1 charge here. X equals 4. And then we want to have an additional smaller +1 nanocoulomb charge. It's going to be +1. That we want to place somewhere such that the net force on it is equal to 0. Okay, so let's try to like kind of think about like where we could place this charge, right? So, for instance, if I were to put the charge somewhere in between these two, let's say like we put it here, for instance, okay? Let's say this is, let's call this charge 1. Let's call this charge 2. And then let's call this thing like charge 3. I should have used a different color for it, whatever. Okay. So if the +1 charge was here in between, then from the +3 charge here on the left, because these are the same charge, right? We would expect F1 on 3 to push this thing to the right, okay? And then since these ones are opposite charges, we would also expect charge 2 to pull charge 3 to the right. So you would end up getting F1 on 3 pulling to the right, and F2 on 3 also pulling to the right. This is obviously impossible, right? For the net force to be 0 on this charge in between these two. Because anywhere you are in between, this one's going to pull it this way, and this one is going to push it away also towards the right. So we know we can't put it there. Okay. We could maybe think about, however, let's say charge 3 was on here on the right, okay? In that case, we might have a case where this works, right? Because charge 3 in relation to charge 2, since they are opposites, will now feel an attractive force. So this would be F23. Whereas from charge 1 all the way over here, it would feel a repelling force, which would be equal to F13. Okay, this is a case where maybe we could have the two of them cancel each other out. And then if we look here, this might happen as well, although I'm tempted to believe it won't, because now the -1 charge is so far away that any attraction that it tries to provide, right, will get overcome by this repelling from this one being like more charge and closer to it. The other key thing here, right, when we learned about Coulomb's law, is that the force is an inverse square law to r squared. So as you like double or triple the distance away that you are from an object, the force will drop by like a factor of 4, factor of 9. So the force, the Coulomb force, drops by like the square of the change in the distance. So in a case here where I say like, oh, well, you know, these two would repel each other, right? But then this one would attract. The issue is that the attracting one is less charge. It's really far away. So any amount of like attraction it tries to pull this way is probably going to get beat out by this thing having a much bigger charge, being much closer and repelling it further. So that's how like intuitively you can be like, I don't think this is going to work on the left side. You could do the math to figure it out, but just to save ourselves some time. So I think something over here is probably going to work. But let's like do the math and make sure it does. Okay. So if we wanted to look at the force of 2 on 3, right? Okay, that's going to be an attractive force to the left. So I would say F2 on 3 is going to equal to K. And then it's going to be Q1, Q2. Okay, so that's going to be 1 times 10 to the, or nanocoulomb is times 10 to the -9. So I'm going to say 1 nanocoulomb, comma 1 nanocoulomb. And then this is all over some distance. And here's what I'm going to do. I'm going to call this 0, okay? So this distance here, which is r, this is x equals something, right? We know that the distance x minus 4 is equal to r, the distance between these two charges. So this would end up being x minus 4 squared. And then what I'm going to do is I'm going to put a negative sign on this. So technically Q1 and Q2 have their own charges. The issue is that whether one's positive and whether one's negative will kind of start messing with you if you're trying to figure out which direction it's moving. So I tend to just make these charges positive and then in my mind say, okay, well, which way is this thing getting pulled? And so if this is a positive charge, we know it's getting pulled to the left. The issue is that, right, if I put positive here and negative here, yes, F2 on 3 is negative. That makes sense. But if I'm trying to figure out the force that charge 2 feels due to 3, that would also come out as being negative. But that's not right. This one feels an attractive force towards the right. So I warn students, like, don't blindly start putting positives and negatives in here. Instead, look at the situation and determine, you know, is it going to the right? Cool, it's positive. It's going to the left, then it's negative. Okay, so this is going to be a negative charge to the left. And then the force 1 on 3, so the force that this charge 3 feels from 1, which we know is going to point to the right because they're the same charge. They repel each other. That's going to be equal to, again, K. And this is going to be 1 nanocoulomb, 3 nanocoulombs. Then over the distance between the two, well, the distance between the two is just going to be x, right? This is x equals something. So this whole distance here is now my r. So this is going to be over x squared. And that's pointing to the right. And then we know the sum of these forces is equal to 0. If the net force is 0, so I can say like F23 plus F13 must be equal to 0. That plus that. And so what you end up getting is, let me copy this in. Okay, some things can cancel. We can immediately just get rid of the k's, right? Divide everything by k. And then we could move this whole thing over to the right because it's a minus sign. And so what I end up getting is, I would say like 3, and then this is like times 10 to the negative 9 squared, right? Because you have nanocoulombs. All over x squared is equal to 1 times 10 to the negative 9 squared over x minus 4 squared. This cancels with this. And then I'm left with 3x minus 4 squared is equal to x squared. Which that's going to get me, what's that? So that's 3x squared. And then that's going to be minus 8x, but minus 24x. And then that's going to be plus 16 plus 48 is equal to x squared. Okay, cool. So when you get 2x squared minus 24x plus 48 equal to 0. So we get x squared minus, I'm going to divide everything by 2. 12x plus 24 is equal to 0. Cool. And is this a nice, well, let me see, is this nice and factorable? I don't think it is. No, 2 and 12. Yeah, okay. Well, at this point, you just need to like plug this in your calculator. So there's my calculator. I could do the quadratic equation. I'm going to show you how you just do it real quick with graphing techniques. So you just do x squared minus 12x plus 24. Trace it. There we go. Oh, cool. We get 2 solutions. Or so what do I want to do? I'm going to do second calc. I want to get the 0. Let's say 0 up to what? I don't know, 5. Okay, cool. 2.54 is one of the solutions. Well, that one does make sense, right? Because 2.54 means that it's here, and there's no way for that to be equal to 0, right? Because this one's going to be pushing this way, and then this one's going to be attracting. So that one doesn't make any sense. This is where you have to be kind of smart when you're solving your quadratic equation to think like which ones physically make sense. You did this in kinematics when you got like negative time sometimes, and you're like, well, negative time doesn't work. So let's calculate the other 0, which is when you're going from 5 to 10. Cool, and that gets me 9.46. That makes a little bit more sense. Okay. So x is equal to 9.46 centimeters. Okay, cool. So that says, like, yeah, somewhere over here is where you would get the net force equal to 0. Let me double check. The math was fine there. Sometimes I get my math wrong, but I'm pretty sure I'm good. 1, good. 3, x squared, x minus 4 squared, x minus 4 squared, so x squared minus 8x plus 16, but then it's plus 48. Cool. X squared, good. 2x squared divided by 2, x squared minus 12x plus 24. Yeah, okay, cool. Good. Yeah, the reason why you get that answer, the 2.46, it doesn't make sense, it's because of the x squared here, right? That forces, it kind of gets rid of the negative thing that you're talking about. So you have to look back at your picture and be like, does 2.4 make sense? And the answer is no. Because again, in that case, this thing's being pushed to the right, but it's also getting pulled to the right. And so there's no way that the sum of the forces there can be 0. And yeah, it's this r squared term. This r squared term here ends up messing up a lot of, if you're just going by the math, like positive, negative, does this make sense? It'll screw up. Yeah. Okay. All right. So knowing that, let's do, there's a clicker question here where now we're going to do things in like 2 dimensions. Okay. Okay, that's that. And then let me get the answer choices for you guys. Okay. So it says, consider the charge distribution below with Q1 and Q2 both being negative. Okay, so these are both negative charges here. Which of the arrows best describes the direction of the force exerted on a positive charge? Oh, cool. At point X here. Okay, so now you have a positive charge here. And again, let's call this like Q3. Okay. So when figuring out the forces exerted on Q3, we have to add up all the forces that it is interacting with, like through the different charges. So Q3 is going to feel a force from Q2. It's also going to feel a force from Q1. Now, between Q3 and Q1 and Q3 and Q2, these two are opposites, right? You got positive and negative. So that means they're going to be drawn towards each other. So if I wanted to draw the forces acting on Q3, well, due to Q2, that's going to be this. And that, so we're going to say that is force 2 on 3. And that's going to be equal to K. And then again, that's like Q2, Q3 over R squared. And that's in the direction of R hat, which means it's in the direction of this towards this. Do they say, is this a... Oh, and this is also an equilateral triangle. This is kind of cool here, right? So that tells you right away that all these angles are 60 degrees. Okay. But that's not the only force acting on Q3. You also have Q1 acting on Q3. And so that's going to be another arrow. Let's make sure we get like the same thickness. And I would say that's F1 on 3. Which again will be equal to K Q1 Q3 over R squared. And that's also in the R hat direction. R hat direction is pointing directly between these two in these two directions. Okay. Now, we said that Q1 and Q2 have the same magnitude, okay? So that means when I'm writing this, I can let's just say like Q1 equals Q2 equals Q. I can now write that F13 will be equal to K, let's just say Q3 over R squared. And then here, this would be equal to K Q3 over R squared. So what you should notice here is that the magnitude of the forces, like F1 pulling on 3 and the force of charge 2 pulling on 3, they are going to be the same magnitude. So they have the same strength of force pulling on Q3. However, they're pulling in different directions, right? So F23 is going to have some components to it. And this is where you have to look at your diagram and create some geometry here. So we could say, for instance, that F23 will have some negative component. And again, if this is 60 degrees, that tells you this right here is going to be 30. Right, this is going to be, let's make it a little bit smaller. 30 degrees. So if we wanted to break up F23 into components, right, we could say that like F23y would be equal to F23 cosine of 30 degrees, right? Because if this is a right triangle, the y component is the adjacent of that triangle. And then this is also negative, right? Because it's the force is pulling down in the y direction. And then F23x would be equal to F23 sine of 30 degrees. Okay? And then that component, right? So since this is pulling down and to the right, this is going to be a positive amount. Now for F13, you have the same, kind of the same little geometry, right? The only difference is that the x direction is going to be different, right? So in the y direction, you have the same thing here. F13y is going to equal to negative F13 cosine of 30 degrees. And F13x is going to equal negative F13 sine of 30 degrees. Because between 1 and 3, this is pulling down and to the left. So it's going to have a negative x component in addition to a negative y component. This one had a negative y component and a positive x component to its force. When you're calculating the net force on this object, it's the same thing we did in kinematics. So what you're going to do is you're going to add all the forces in the x direction, and then you're going to add all the forces in the y direction to then get like a resultant like super vector force on it. So if I want to say like sum of forces in the x direction, sum of forces in the y direction, okay? In the x direction, we have this. So you have this one. So you have F23 sine of 30 degrees, and then you have minus F13 sine of 30 degrees. And then these add up together. Now, the cool thing is that, remember that F13 and F23 are the same thing. It's the same magnitude. These are the same. So this ends up getting that your sum of forces in the x direction is going to be equal to 0. That kind of makes sense, right? By symmetry, the amount of force here pulling it to the right is going to equal the amount of force here pulling it to the left. So you're going to get 0 pulling force in the down direction. Okay? Or so in the x direction. Left and right cancel each other. If we look at Fy, however, right? Now I have negative F23 cosine of 30 degrees. And then you also have a negative F13 cosine of 30 degrees. So this ends up equaling negative 2F. Here, we can just say, yeah, because F13 equals F23 cosine of 30 degrees. And so this is, what cosine of 30 is, square root of 3 over 2. So this is just equal to negative square root of 3 F13. Okay. So my total force acting on this object is 0 in the x direction, but negative in the y direction. And so the correct choice for that, so they don't ask you to calculate a number or anything. You will need to calculate a number on your homework and for sure on a test. But the answer there is going to be down. So let's check out here. So this should have been answer choice B for question 1, right? Let's check. And that's correct. Good. Okay, I'm going to take a second. Does this make sense how we did it? So whenever you're finding the net force on a charge, you need to consider all the individual forces from the surrounding charges. And you need to break up those forces into components. And then you need to add all the components up. So all the x components from all your charges, and then all the y components from all the different forces from different charges. And then you get a resultant force. Okay, cool. Awesome. All right. Ooh, okay. So now we're going to change the geometry up a little bit. Let's see, question 2 here. And again, these are pretty simple to solve just by like symmetry, geometry arguments. Yes, for rough approximations, you can solve visually, 100%. Yeah, if the question asks you like just what direction, you don't need to do all the numbers. I wanted to do the numbers to just show you like during lecture what you'll need to do for like a homework question or for a test question, because in your homework and your tests, these are usually not the same charge. So these magnitudes are usually not the same, which makes it a lot more work, but the process is the same. But yes, if you have symmetry arguments, Fedekai, you don't need to do all this work. You can just say, oh, by symmetry, the x components cancel out, the y components, add up to each other. So that means it goes down. So we can see here, I think here we can probably make a symmetry argument. So let's see. Two charges of equal blah, 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 yeah, are separated by distance s. Consider the positively charged place at this one. Oh, and we say this is positive. Okay, cool. Oh, so this is a nice little follow-up. But we've kind of already done this. The only thing that's going to change is the direction, right? So this is a positive charge Q. Okay. So again, the other thing that made sure that these forces were the same, like the magnitude of this arrow was the same, is that they were also located the same distance. So we had equal charges here, and we also had the same distance. If either of those things change, then you can't make symmetry arguments, because the magnitude of your force will change. So here, yeah, same distance. That's cool. This, we know, is going to repel, because these are both positive charges. So we're going to end up getting, I can say, like, some force. And this would be, again, let's call these different numbers. Let's call this 1, 2, and 3. So F 1 on 3 is going to point that way. And then between these two charges, these are opposites, which means they're going to attract. So charge 3 compared to charge 2 is going to feel a force towards it, right? And so that's going to feel this amount. And we say that's going to be F2 on 3. Now, because the magnitude of the charges are the same, the signs are different, but that's okay. Because the magnitude of the force, right, is equal to like the absolute value of K, Q1, Q2 over R squared. Since one of the charges is always the same, and then these are the same magnitude, they're just different directions, the magnitude of the forces will be the same. Also because the distances is always just S. So S, which is like the same. Now you can make like a geometry argument. You can say, okay, well, this pulls some amount up, and this pulls the same amount down and to the right. So the components of this in the y direction are going to cancel. So this amount is going to cancel out with this component. I didn't draw it to scale, but these are going to cancel each other out. And so all you're going to be left with is the, kind of like the positive interference of both of these now pulling it to the right. Yeah. So you can totally use symmetry for this one. And let's see. Pull up the answer for this one. So for question 2, the net force is going to be pulling to the right. And so if we go check that out here, that should be choice C for question 2. And that's correct. Nice. Okay, good. All right. That was good. All that made sense. And everything was correct. Nice. Okay, cool. I don't think I want to get right into electric fields yet because that's a totally new topic. We'll save that for tomorrow. Are there any questions about this so far? We've done some pretty simple cases. As you'll see later in the homework, and definitely as you go through the chapter, it gets a little bit more complicated. It's just more tedious is all it really is. So if we go into if electric charges and fields wants to load today, yeah. They have, for instance, stuff like this, which is like a nightmare, dude. What? Why would you want to do that? It's 7 different charges? I don't want to do that. I think here, this is like kind of a decent example of you have different charges that are located different distances, right? And so you end up getting a resultant force that isn't some nice like symmetry argument. You have to do the individual forces. You have to break them up into components. You got to add the components, and then you got to do, the good old Pythagorean theorem to figure out what the magnitude of your resultant vector is, and also what the direction of that is. You must have done this in kinematics, I'm sure, doing like resultant force and direction. You do like arctan and stuff on it. But okay, cool. All right, I'll let you guys out a little early today because I went over time previous lectures, but our office hours today is going to be in about an hour and 20 minutes. So if you have any questions about the homework, I think one of the homeworks is due soon, right? Let me see real quick, like what homework was. I think one of them is due today. Yes. So yeah, mechanical waves is due today in 20 minutes. So please do that. If you have any questions about the sound and music homework, which is due Wednesday, come to office hours today. I'll go through and help you out with them. Otherwise, we'll have our lecture tomorrow, same time, same place, and we'll finish up electric fields. And I think you also had discussion as well, so make sure to do your discussion assignment too. Okay? Okay, cool. All right, that's it for today. Enjoy the rest of your Monday. Good start to your week, and we'll see you tomorrow.